angular kinematics is homework 8 as well. Homework 9 will be all about torque and rotational inertia. Kinetic energy of rotation and angular momentum will be homework 10. So basically, if you wanted to carve out what was on the what's on the second exam, it's the tail end of forces, energy, momentum, center of mass, angular kinematics, which is largely a repeat of the regular kinematics, and then this, and the homework 10 and beyond will be on the final exam. In fact, pretty much most of the course is on the board right now. Why don't we, while we're at it, just make it a complete set. Homework number 10 at the end will also contain oscillation, something called simple harmonic motion. Homework number 11 will take our ideas and apply them to fluids. And then homework 12 will be waves. So this right here is the entirety of Physics 1. Okay? Obviously, there's a lot to be delved into in each particular thing, but this is the grand overview of this entire course. Okay, so are there any questions before I move into angular kinematics? All right, so let's do it. This stuff is so similar. It's amazingly, there's only a few little adjustments we have to make here and there, and we're pretty much good to go. Let me remind you how one-dimensional kinematics worked when we're talking about linear motion. So along a line. So these are the kind of problems that basically the entirety of your homework numbers 1 and 2, or sorry, mostly homework 2 and then homework 1, whichever things weren't like totally introductory, like units and stuff like that. So what you have some initial location, you have some final location. You can talk about the displacement between them, displacement. You can talk about the velocity. And typically in our purposes, we, of course, talk about the initial velocity, the initial instantaneous velocity, the final instantaneous velocity perhaps, or maybe even VAV, which might be the average velocity. So you have VAV and you have instantaneous velocity. We, of course, talk about the acceleration that you may have. That's what changes the velocity from one value to another. And we said things like this. If the velocity and acceleration are in opposite directions, what happens? You slow down. But if they're in the same direction, then what happens? You speed up. And then, of course, we had the constant acceleration equations, which were really this master toolkit where we combined lots of different things and had it immediately accessible for quick problem-solving strategy. Now, all of this stuff is expressed with meters. So we have meters for displacement, we have meters per second for velocity, and we have meters per second squared for acceleration, right? So let's go ahead and now write down angular kinematics. So we're going in a circle. So you might think, well, this going in a circle is much more complicated, but a circle is a highly constrained motion. Once you know you have to move in a circle, you can only go one way or the other way, counterclockwise or clockwise. We only have two choices in motion, just like we have two choices of motion in the x-axis, right? In the x-axis, we can go right or left. Circular motion, we can only go counterclockwise or clockwise, right? So here, along a circle, we can simply apply the same exact ideas. Now, by convention, we take that counterclockwise is positive and clockwise is negative. Now, if that seems counterintuitive to you, of course, we watch a clock all day. I don't know, maybe you have a digital clock and you don't really care about this, but a clock goes clockwise, hence the name, right? So time goes forward. You might be more intuitive to call that the positive direction, and yet we're calling clockwise negative. The reason for that, basically in math class, lots of things are talked about clockwise or counterclockwise. For instance, if you have the quadrants, x, y quadrants, look at how they're numbered. First, second, third, fourth quadrant. So in math class, counterclockwise is a little more of a natural direction. So that's why we pick counterclockwise to be plus. So from here, all we do is do the same thing. The angular displacement, we're going to generally measure it in radians in terms of pi. So instead of talking about how many meters our displacement was, we'll talk about how much angle our displacement was. So you could certainly talk about it in terms of degrees if you wanted to. So your displacement was 30 degrees or 40 degrees or whatever. But as I mentioned on the first day of class, degrees is not an SI unit. So if we're going to try to do anything with that, we're going to get in trouble. If you notice all your calculations thus far, the degrees was kind of you never did anything with it except take a sine or a cosine of it, or tangent or inverse tangent or whatever. And as long as your calculator's in the right mode, it'll work it out for you, right? You notice we never did anything with an angle that didn't involve a sine or a cosine or a tangent. And then as long as your calculator is fine with that and knows what to expect, you can get away with the non-SI units of degrees. Now, we're going to get serious about doing stuff with rotation. Sometimes we'll use the angle without a trig function. And we better be in radians. Radians is the SI unit, okay? Another thing that I should mention about this, be careful. If you go in a circle counterclockwise like this, you might be tempted to say that the angular displacement is 0 because you wound up at the same place, but you don't get credit for that in circular motion. Circular motion, you're always going around and around in a circle. What we would say here is that this angular displacement is plus 2 pi. So 2 pi because it's one full circle, and plus because you went around counterclockwise. The only way you can get away with saying that the angular displacement is 0 is if you did something like this. You went one way, and then you came back. Then you could say it's 0. This is just to keep things in line in perfect analogy with the old stuff, right? If you were talking about a straight line, the only way you could end up with 0 displacement is if you came back, right? And ended at the same place. But you could never only travel in a single direction and somehow wind up with a displacement of 0, right? That's impossible on a straight line. We like to say that if the velocity is always in one direction, then the displacement is going to be that direction. So you have to be careful. This is where it gets to be a little bit of a translation problem between the circle and the straight line. For the circle, if we want to make things as analogous as possible, we can't get credit for coming back around. So if you go full around a circle, the displacement is plus 2 pi. If you go counterclockwise, not 0. Okay? In order to wind up with a displacement of 0, you have to go and then come back the same way. Okay, so we can talk about angular displacement. How much angle have you covered? VAB is, of course, displacement over time. That's how you also define average angular velocity. Is how much angle you've covered per time. It's measured in radians per second. So on average, how much angle did you cover per time? It's all the same stuff. And by the way, I guess if you're not familiar with these Greek letters, this is omega. It's a lowercase omega. It's a rounded off W. It's not a W. So I know some people already write a W like that, but W has sharp corners to me. Okay, this is omega. And then this is alpha. That's going to be angular acceleration. So just like you can talk about your velocity on average, you can also talk about your instantaneous velocity. You can also talk about what's your instantaneous angular velocity. So at that moment, how much angle are you covering per time? And then finally, instead of acceleration, we talk about angular acceleration. The units for that would be radians per second squared. So it talks about the rate at which you go faster or slower in terms of angle. You can also say things like, if these two are in the same direction, you speed up. And if they're in opposite directions, you slow down. And of course, if there is no angular acceleration, you'll maintain your angular velocity, right? So it's all exactly the same stuff. It's almost like we're just making a weird change in variables, right? We're changing the variables to these weird Greek versions, and instead of meters, everything's in radians. So instead of talking about physical distance, we're talking about angle. We can even write down the constant angular acceleration equations. All you have to do to make these is just copy each thing into its angular counterpart. I guess let me do that over here. These are the constant alpha equations. 1, 2, 3, 4, 5. There are 5 of them. These are not even included on the equation sheet because they would just be a big waste of space. All you have to do to make them from the ones that are there are to replace delta x with delta theta, replace v with omega, replace a with alpha, and you are good to go. Okay? So I guess let me go ahead and write them down just so you can see them. And I will also post, I can't remember if I did already, but I'm going to post an angular kinematics summary sheet for you so that you have these for your reference. Here's what they look like. So the Bizarro version of equation 1, equation 2, equation 3. They hopefully have a familiar look to them because they are just kind of weird versions of things you already have used a bunch. There you have them. And for reasons that I'd rather not get into, they're typically written without the vector hats in these equations, but you should put in signs. So just like it was before, signs go in, signs come out, right? So these equations are signed. Put in positive for things that are counterclockwise, put in negatives for things that are clockwise. Put them in the input, and if you get a sign on the output, it means that too. So if you get a positive on the output for any of these vector quantities, it's counterclockwise. If you get a negative on the output, it is clockwise. The only thing that should always come out positive is what? Time, of course, because time is not a vector. There's no such thing as counterclockwise and clockwise time. Time only progresses in one direction. I guess just to even complete the picture, let me add that column, the missing column, right? Which each one is missing. So this one's missing displacement. This one's missing final velocity. This one's missing time, acceleration, initial velocity. The problem solving strategy is exactly the same. You have your 3 required minimum variables. Ask for a 4th, don't know, don't care about a 5th. All that stuff, right? It all works exactly the same way. The only difference is that it's plus and minus is counterclockwise and clockwise. That is a convention, but that we will use exclusively. So this will be our convention in this class. That's not really up for negotiation, so sometimes the homework will expect you to put in a plus or minus. So all the warnings, the prominent warnings on top of homework 2 and 3 about how sign is in the eye of the beholder, so don't expect WebAssign to read your mind and realize the negative is downward, because it isn't. It's, if you want to call it that, that's fine, but it's not universal. For this, we are going to use those universally. So you can consider clockwise and counterclockwise to have those signs attached to them, okay? Okay, so these are all well and good, but right now this is kind of an island of alternative language describing things in terms of angle, which is not connected to our current ideas that we were talking about before. So the question is, if we're on this kind of isolated island where everything is discussed in terms of angle, what is the connective tissue to talk about how does that relate to the old physics? Because obviously if something's going in a circle, there is also translational motion associated with that. You are still covering meters per second, even if you're covering radians per second, right? So that's the next thing we have to do, is to figure out what's the connective tissue between this and our old physics. So let's talk about that. Let's see how far we can get today. Probably not very. So for our angular kinematics, it's all in terms of angle. What's the connective tissue between that and the old physics? The translational motion. So let's start back at the beginning at angular displacement. If we travel from point A to point B on a circle, that certainly involves traveling some angle, but there is also a distance covered here, right? I'll call that distance S. So if S is a distance, that's measured in meters, whereas if delta theta, that's an angle, which I will suggest is measured in radians. So the relationship between these two is the arc length equation. The extra ingredient you need is r, the radius. So the equation is S equals r delta theta. Is this an equation that's familiar to you from math class, arc length? Well, you probably know its most famous special case. Let's say it's not just some fraction of a circle, but it's all the way around. What do we call the distance all the way around a circle? Circumference. And what's the formula for circumference again? 2 pi r. That's a full circle is 2 pi radians. So circumference equals 2 pi r is just a special case of the arc length formula where it's not a fraction of a circle, it's all the way around. I do want to point out, however, that circumference is not 360r, okay? That doesn't work. And yes, 2 pi is one way to describe a circle, 360 degrees is another. You could even say a full circle is 1 revolution. But circumference is not r. So this is wrong, this is wrong. You can see why we need to be in radians. Because now we're using the angle raw without having it be inside a trig function. So that's why we have to be in radians. Now, if you look at radians, s is a distance, r is a distance too. So delta theta, which is in radians, that's really actually unitless. Radians is a fake unit. Radians is not a real unit. A radians are ratios. It's ratios of distance traveled to a circle, along a circle, to the radius of that circle. Okay? If you want to see what a rad is, here's what a rad is. If this is the same distance as this, so r and s is equal to r, that is 1 rad. So now you know what rad is, okay? A rad is like a piece of a pizza where the distance along the crust is the same as from the crust to the point. That is 1 rad, when the ratio of the distance to the radius is 1. And if you go over here to the formula here, circumference is 2 pi r. We can solve for pi. Pi is circumference over 2r, or circumference over diameter. If you take the ratio all the way around divided by the distance across, you get a ratio that's transcendental. It's a number that never repeats and never ends. 3.1415923585858, 3.141592653589799. That's all I got. Okay. They have contests where they memorize this to 100,000 digits and they recite it for over 8 hours. If it's brute force memorization, there's no pattern. Okay. Something as simple as a circle, you measure the distance around to the distance across, you get this number. Okay. So 1 rad, that's easy, but when you go all the way around, you get transcendental. Okay, let's leave it there for today.